first of all, I would like to welcome you to this program, being connected by NITR Chandigarh.
So I'm Sneha. I'm the technical team lead for FEA, working in ARK Info Solutions, and he is my colleague Somil. He is working as a finite element analysis engineer at ARK Info Solutions.
Hello.
So we will just start the session. I will just start with what is finite element analysis. So I guess people are familiar with what is finite element analysis. So let us say we are all are mechanical engineers.
No, ma'am.
All are not mechanical engineers. Okay. Let us say I want to construct some beam, or let us say I want to design one chair. Okay. So to design a chair, so what I will have to see about that, I will have to look at how it should look like. I will have something into my mind that my chair should look like that. It should have some features, like let us say it should be lightweight. Otherwise, I will see the aesthetics of it. And the most important, that biomedically it should be good. That by sitting on a chair, no of my body area should get pain. So this will be my minimum requirements. And other things are like we will put some kinematics into that, right? It should rotate into 360 degrees and all, right? So to do that, so I have different methods to design my chair and actually put it into the manufacturing unit. So one thing I can do experimental study, what our carpenters do. They will design a chair, they will do that what carpenters do. They will design and then they will see whether it can sustain a load, whatever, let us say 100 kg of man, or let us say 80 kg of man. So it will try to see, so that will be the experimental analysis of designing, or by seeing any object into that, so how it will sustain the load, or what are the expecting, those are visible into it or not. Another way of doing that is called as a analytical method, where we put some formulations into that. We actually find out what will be the stress coming into it, what will be strain into it, what will be the life of my component of my chair. So that I will see by analytically. But for that, chair itself is not a very simple design. It has different joints, it has different features, different parts are there. So what happens in this case, you will need to do a lot of work into it, that you need to formulate the things, then you will have to do it by your hand, or you will have to put it into some softwares like the coding, what we call, and we will have to run that code. So this, whatever process is, the experimental process is time consuming, as well as this is cost is being, a lot of cost is being expended on experimental things. So, and in what is the drawback of analytical method is the time, that we are consuming lot of time for doing some simple analysis. Then people came up with an idea called as finite element analysis, that is nothing but a numerical method. Now there may be a doubt into your minds that numerical method is not an exact method, it is an approximate method. But the accuracy of any of the numerical method can be increased. So people came up with an idea called as a numerical techniques. So finite element method is nothing but it is based on a numerical method. And if I will strictly talk about ANSYS software, the Newton-Raphson numerical technique is used behind ANSYS software. So how the accuracy, how I can increase the accuracy of my any of my simulation, let us say optimization, that I will increase the number of iteration. By increasing the number of iteration, I will increase the accuracy of my design or of my simulation. So this is what the finite element analysis background But actually finite element analysis is what? Once you will have to do that, you will have to virtually you have to design your chair or whatever may be your component, you have to virtually design into the software. So ANSYS has two design tools. One is a space claim and another one is a design modular. Even if you have designed your whatever object is that, you can import your design from any of whatever designed in other software to the ANSYS. So this is the benefit of ANSYS, that you can design, you can import the files which you have designed in other softwares. So whatever design is there, so finite element method, what it does, it will discretize or it will divide your structure into number of small elements. So that is a discretization technique we call is a meshing. So, and the heart of any simulation technique is a meshing. So whenever we are going to do any simulation into ANSYS, we will have to follow some steps. I will just give you 2 minutes. I will just quickly show you what are those steps. So whenever we are talking about ANSYS, there you will have, there are different physics can be solved inside ANSYS. That is structural, fluid, thermal, electromagnetics. In structural, you can do linear as well as non-linear analysis. In fluids, you can go with steady and steady flows as well as compressible and incompressible flow. In thermal, you have all thermal physics like conduction, convection, and radiation. So this is the capabilities of ANSYS I am showing over here. So whenever we are talking about ANSYS, it or FEA, it can be applied for structural analysis. It can be used for solid mechanics, dynamics, thermal analysis, electrical analysis, as well as biomaterials like human organs and tissues. So actually today's agenda is more towards optimization. So I will just quickly show what are the different capabilities of ANSYS where you can use your optimization techniques into it. In structural analysis, you can do, as I said, you can do linear as well as non-linear analysis, as well as you can see the failure criteria like creep, fatigue. So you can interpret those results into your software, as well as you can see, let us say, you will be thinking that only metals can do, but ANSYS has a good range of material handling, different engineering materials capabilities, like it can handle elastic materials, plastic materials, as well as hyperelastic, that is like your rubber materials. It can handle different phenomena like creep, fatigue, as well as your different failure criteria. It can predict your life cycle of your object, as well as it can tell you how you can improve your life that through optimization. So optimization can be done into ANSYS, into your physics. Similarly, you can handle your thermal analysis, that is all your phenomena like conduction, convection, and radiation. ANSYS can handle easily offshore applications where you have a structure which is into a fluid. So ANSYS has a good capability of handling multi-physics domain, that is any structure with, as you can see in the video, there is an offshore application is there, right? So in that, there was structure is there which is inside a fluid domain. So where whatever the forces coming onto your structures are due to the fluid domains around it. So you need to do fluid analysis, as well as by doing the fluid analysis, what are the different stresses coming into your structure. So this is the best on two physics, that is structural as well as fluids. Handle this as well. ANSYS can also handle dynamics and kinematics. Kinematics means where we are more concerned about the velocities and accelerations of our structure or our joints. So ANSYS can handle this as well as dynamic simulations, like where it is dependent on time or it is independent of time. It can handle vibration characteristics, your free vibrations as well as forced vibration characteristics. ANSYS have a explicit dynamics which we use mostly into a safety analysis applications, as well as we can do a drop test into ANSYS for different devices like your mobile phones, your laptops, and the safety applications or crash analysis of any vehicle or aeroplanes. This is an example what we have done at our end for a drop test, that is a drop test of mobile. ANSYS has the capabilities of running a CFD. So as today's topic is more concerned about the optimization, I just wanted to give a essence of what is finite element analysis and what is ANSYS. Okay. So now let us move towards optimization. So what is optimization? Monica, can it be interactive? Hello?
Yes, yes, yes.
Yeah, is it interactive means can I interact with the participants?
Yes, yes, ma'am.
Yeah, so I just wanted to know that what is the idea of optimization into their minds?
Optimization is more or less finding out maximum or minimum value
Okay, I'll take care.
for a certain equation.
Sneha, we have participants from interdisciplinary, electrical, mechanical, maybe civil engineer, electronics, computer
Okay.
also. So it has to be generic talk.
Okay, fine. No issues, sir. Fine.
Okay.
So I will only continue. Okay. So come back to what is an optimization. It is nothing but it is a problem in which certain parametrics. Now let us say I am talking about any design. So we have some goals into our mind that my structure should be like this, or some fluid people may be thinking of that this should be the outlet pressure velocity of my flow. So this is should have something go into my mind. So what optimization plays is it is setting you towards your goal. So we called it as a goal-driven optimization. So optimization is nothing but it is a problem in which certain parameters needed to determine to achieve the best measurable performance under a given constraint. So whenever you think of any of your, since I'm from mechanical background, I can tell you the mechanical physics, but I will take simple examples. Same example we'll take of a chair that anybody can visualize of. So let us say I have already told you what are maybe my expectations of having designing a chair or manufacturing a chair. So I have certain goals into my mind, but when I virtually design my chair into my software and when I apply different types of loads, I will get failures into it somewhere, maybe at joint or maybe at its foot or somewhere I will get failures. So optimization techniques are there where you can reduce your cost as well as avoid failures are happening. So how it will help you? So you will come to know when we will talk about different slides. So what is the need of optimization? When we talk about a design perspective, that is, it should give, as a designer, one thing in my mind that my design should give a best performance. Maybe it is whatever the structure or whatever may be my system. It may be a one chair or it may be a group of chairs or it may be your whole aircraft as well. So as a designer, my aim is to have my structure which will give the best performance. into air, main requirement is it should have low weight and high strength. So I should have those optimal materials which will increase the strength of my aeroplane, and by the time it should have a reduced weight. So these are some examples where we talk about the optimization. Now this is as a design engineer. If I am a planning, so there is a production planning. When I talk about the production planning, I should have an aim that my manufacturing cost should be as low as possible. So what are the different aspects where I can reduce the cost is called as a cost optimization. Similarly, I have a finance resources where their aim are having, they should have maximum profits to whatever you have designed. So to have maximum profits, the initial thing is it should have minimum manufacturing cost. So this two goes hands in hand, that you should go for a cost optimization. As you can see the flow, everything is related to each other. When I talk about the task of planning, that is again I should have a good performance of my structure. When I go to control and manufacturing, there should be all control parameters are giving a best performance. Let us say it is a machine. Let us say it is a machining process, lathe machining or welding, different processes. So whatever my design is there, whatever my structure is there, when I put some technical inputs to that, it should work fine, it should perform very well, and it should, at the robotics, it should be good. And the most important part is mathematical modeling. That whenever people are doing any research, or if any of the, when you are making a patent, when you are making a patent, you are paralleling your work, studying that you are analytical or you are in finite element analysis or any of the analysis tool, you are doing your job as well as side by side, you are doing a study that should match with your numerical or mathematical study. So here your all curves fittings as well as surface fittings should have a minimum error when you are doing a comparative study. So in ANSYS, yeah, sure.
I am from Suresh Gyangar University, Jaipur. I want to ask today's lecture. It's on ANSYS. We are doing the optimization on ANSYS or on MATLAB?
ANSYS.
This is ANSYS today.
Yeah, this is ANSYS today.
Okay, so on MATLAB, it will be done tomorrow or something?
Tomorrow we have a session on MATLAB again.
Okay. Okay, thank you.
Shall we proceed?
Yeah, please continue.
Yeah. So in ANSYS, when we see there are different types of optimization. So the previous slide was well explanatory that what are the different objects you may have, and now this slides tell you how you can fulfill your objectives into ANSYS. So it is having, basically it is divided into three categories. One is a structural optimization, second is a parameter optimization, where we have two different interfaces. One is a design explorer and another one is a ANSYS OptiSlines. And third one is a non-parametric optimization, where you have structural analysis, topology optimization and design validation. So we will go one by one. So first is a structural optimization in ANSYS Workbench. So first, when we talk about a structural optimization, there are three types in this optimization. One is a size, another one is a shape optimization, and third one and the most important is a topology optimization. So what is sizing optimization? So it is also known as structural connectivity and known as the cross-sectional optimization as well, where you change your cross-sectional size of your structure, you optimize the cross section. So in a picture you can see there is one truss over here, right? So let us say the diameter is some mm or some meter, some centimeters is there. Okay, so when I talk about size optimization, I will increase or reduce the radius of my cross section of my member. Size optimization. So I will try, I will have a trial and error that I will put into the ANSYS different radiuses, 5 mm, 10 mm, 15 mm, 20 mm. I will put some iterations. I will get to know which is the optimum radius which is suitable for my truss. Similarly, second type of optimization is called as a shape optimization. As in the first, I changed only the radius, that is, I changed the sides of my cross section. In second kind of optimization, what I will change the different cross sections and I will test my truss by taking different cross section. Let it be like circular, rectangular, I section, Z section, C section, and I will find out what is the optimal design or optimal cross section suitable for my truss with having some different loading condition. And the third and the most important is a topology optimization. This is an unknown connectivity. This is an unknown structural connectivity, shape and size optimization. So it is comprised of shape and size, as well as it will work on the unknown connectivities between the structures. So we will discuss topology optimization in depth in the next slides. Next type of optimization is parametric optimization. So in parametric optimization, so the next is we are talking about structural optimization is over. Now we will talk about what is the parametric optimization. Then parametric optimization, we will study the design of exploration, response surface fitting, sensitivity, correlation, optimization, and Six Sigma techniques or Six Sigma analysis. So when we talk about, this slide is missing. Okay, yeah. When we talk about a design explorer in ANSYS, you have design explorer as an optimization tool. So where we study different parameters which you can see on this slide. That is, it shows what if study. That is, in what if studies we are doing lot of trial and error methods. So basically your ANSYS design explorer is based on ANSYS parametric pack. Means the software which is running behind the ANSYS software is called as ANSYS parametric pack, and design explorer takes care of your parametric study or your optimization study into ANSYS. So Design Explorer is a powerful approach to explore, understand and optimize your engineering challenges. It may be your design related, or it may be your structural related, it may be your fluid flow related, it may be electromagnetic related. So any of your engineering challenge, ANSYS can handle those challenges within a branch called as a Design Explorer. So what it does, it determines the key parameters influencing that design. So it will see which are the parameters which are influencing my design, where I can optimize my design or I can optimize the structure. It will explore and understand the performance at other design and operating condition. As we can change into the design specification, similarly, You can make changes into operating conditions. Maybe when you talk about a fluid flow, you can change the values of pressure, velocities, and temperatures at inlets. At particular conditions, let us say I'm getting some output. My input conditions are same, but I should get some output which should be the optimum. So I can work on the output parameterization or output optimization as well. It will find the conditions which will give the best performance. So which are the factors which are dependent upon the performance of your design. So it will work on it. It will optimize your performance by changing your different design parameters or your input parameters. And it will explore the robustness into design. At the end of your optimization in ANSYS, you will get a robust design which we do into Six Sigma. So this is a quick chart, a quick flow chart of doing optimization into ANSYS. So these are, you can say, a design explorer features as well. So in the first step is a what if study. In what if study, what we do is we take any, let us say I am having some design. I do on trial and error basis, I do different changes into my design. So I will do, in what if study, I go on doing, if this is my input, what should be my output? If let us say 5 mm is the thickness, then what is the, even we in the next slides, or once I will complete this flow, I will show the demonstration of what if study on my computer. So in what if analysis, this is just a manual study that whatever you think like, so this will come by experience. So what I should change? I should change shape. I should change size. I should change the input characteristics. Let us say for structural analysis, it may be pressure or it may be force or it may be constraints as well, different boundary conditions. Similarly, when we talk about a fluid flow, what I can play with my designs, I will play with the what are the input characteristics or inputs, let us say pressure, velocity, density. I can have a parameterization and what if study over there, that is a manual study. Second, you can say is a sensitivity and correlation analysis where you find the relevant parameters. So this is what actually matters to the analysis and to the output, where we do the correlation study between different parameters which you have put for the optimization. Next, that is the third step is design of experiments, where you identify some parameter which matters and put the design space, that is whatever parameters you have identified from correlation analysis. Now those I will take for optimization and I will put it into the design space for further simulation. The fourth step is response surface, where you actually build a mathematical model into that. So you don't have to build it. Software will do it by itself. So it will do some curve fitting into it. So I guess all are aware of what is curve fitting. So response surface verifies your model with the mathematical model. Next is the optimization. So you can do optimization with or without response surface. That is, we will have an input parameter that can protect the output primarily spaced into the mathematical model. So optimization will do maximum. There are three options into optimization: minimum, maximum, and specific target. So you can optimize your design at minimum level, at maximum level, or you can put some specific target to that, which we call as a goal-driven optimization. So once we are done with this, we go for Six Sigma analysis, where your whatever you have modeled into your answer or into your software, whether it is matching with your what mathematical model, and what when I will manufacture that, so is it matching what I was wishing for. So it will give a robust design into a Six Sigma analysis. It will make sure that something that works into technical growth based on manufacturing and operation handling. So I will show how what if study is being performed. So my colleague will explain you how the what if study is being performed.
So actually, what if study is an approach which you use for optimizing your design manually. Means in this approach, the user is actually unaware about the parameter which he is taking for his study. Based on that, by changing various parameters and the parameter values, he will get a particular complete set of results. But the main disadvantage with this approach is the user is not able to conclude whether the parameters which he has selected are optimum for that design. That means he is not able to justify that those are the only parameters which are affecting the optimization of their design. I'll simply show you one simulation whereby we have used what if approach for designing a simple three-dimensional beam model. Over here, I have designed a rectangular beam. It is a three-dimensional cantilever beam. This is the geometric 3D geometric model of that beam, whereby I have parameterized the dimensions, that is the cross section of that beam. I have parameterize the height and width of that beam. So remember, whenever you parameterize certain aspects of your design, it will be included in a list of parameters set within your. So we'll run a simple case of optimizing your design using what if study. I was talking about what if study. So in this, what we have done is we have designed a three-dimensional model of a simple cantilever beam which is fixed at one end, having a force at other end. So I have just selected the cross section as rectangular cross section, whereby I will just simply parameterize its dimensions. You can see over here I have put a parameterization for height and width. Now whenever you put parameterization by checking on the checkbox next to certain values or certain parameters, then in ANSYS workbench it creates an independent parameter set which will be used as a relation, or rather the relation in the form of equation, which will be used to manipulate your results based on the values which we have given as input. So here I have parameterized the cross-sectional size of the cross-section. So by parameterizing the size of cross-section, what I am going to do is I am actually going to check the effect of the stresses due to that. I am going to check the stresses generated due to that force when I change the size of the cross-section. So it will clearly tell me at which cross section the value of force would be exceeding the limit of that material. So after parameterizing the cross section, I am just simply going to the mechanical module, and over here I have, in order to carry out a mesh independent study, means we will also check what would be the variation in our results by when we change the size of discretization. That is, when we change the size of mesh, as per the change in size of mesh, how my result would deviate. If I want to carry out that mesh independent study, I can simply parameterize the element size. Here I have taken the element size as 5 mm. So I have selected it as a parameter. Now I'll give assign boundary conditions to that model. I have assigned a fixed support at one end and a point force at other end. Now the value of force I have parameterized. Now how to parameterize particular value? You can see I have entered a force in negative y direction. So in order to parameterize particular value, I'll simply check the checkbox next to that value. So whenever you check on a particular checkbox, it will get parameterized. Now what we will do is, for carrying out that independent study using what if analysis, we will simply create a set of varying values of forces and mesh sizing, and based on that we'll get different values of total deformation and equivalent stresses. Now over here we'll just parameterize. We have evaluated the results for total deformation as well as for equivalent stresses. Now I'll simply parameterize the maximum and minimum value of equivalent stresses and deformation.
So for doing parameterization, you can see and whenever you want to parameterize any of the element, it may be dimensions, it may be your different forces, or you can parameterize your results as well. So when you do this optimization or parameterization, so beside of whatever these values, you will see one block over there. So you just have to click on that, check that box where the P, you can see P has occurred, which means that parameterization. Continue.
Similarly, we will parameterize the value of equivalent stresses also to check out the maximum and minimum value. Now we'll simply solve this model. Now you can see it is showing contour plots for total deformation as well as for equivalent stresses. Now what we'll do is we'll just go to the parameter tab. Just simply double click over here. Independent parameter set will get opened. It will consist of the values which you have given as parameters. Here there are 4 parameters. I have selected the height of the cross section, which is 40, the width of my cross section, which is 30, and the body sizing for discretization, that is we call it as meshing, that which is 5 mm. And I also parameterize the value of force in Y component, which is a compressive force of 1000 newtons. Now to carry out that study, these are the input parameters which I have inserted to, which I have given to the software as input, and based on those input parameters you can see downwards these are the output parameters. For time being we won't consider this factor of safety, as I'm going to explain it to you using response surface. Now we'll consider only total deformation, maximum and minimum value, equivalent stresses, maximum and minimum value. So now I'll simply set various design points. For example, if I increase the size from 40 to 45 and width of the cross section also I change, I'll just simply increase the height of that cross section, keeping the width same. And you can see over here, I've also not changed the value of force. I've simply manipulated the size of cross section. So based on that, I'll just update all the design points. So it will give me the results, desired results for the changes which I have made. For example, by changing the height of cross section from 40 to 45 mm, it will tell me what will be the corresponding stresses and deformation for that particular value. So right now it is updating all the values. It will take some time depending on the number of input parameters you have given to your design. Now it has solved for that particular value. When I have changed the height of my cross section from 40 to 45, the equivalent stresses and deformations have also changed. The deformation changed from 0.14 to 0.13. That is, there is a reduction in total deformation and also in equivalent stresses. So, which clearly indicates that by increasing the height of that cross section, by keeping the width same, the stresses and deformation in the body would be reduced. So, this indeed clearly indicates that I am approaching towards optimality. So now I'll just keep the height as same and I'll change the width. Then I'll again update the design points. So this is what is called as what if study, whereby the user inputs various parameters based on his understanding and then obtains the desired results. But this approach cannot tell you that the parameters which you have taken as reference are the only parameters which are creating a change in your resulting analysis. Any doubts up till now?
Monica, is there any doubt? Hello?
Ma'am,
Yeah.
please.
Yeah. This was about the what if study, that for different design aspects, what may be the results, or for if I will do the changes at this parameter, what will happen? If I will change the width, if I will change the depth, if I will change the magnitude of force, if I will change the pressure, so different parameters, as well as if I will change the mesh size, so what will happen? So this is just a manual approach of doing this study, that I will manually check that which study will give me my optimum structure or optimum design parameters. So what do you think? Is it a perfect study? Whatever I have assumed optimization, is it perfect or it is wrong? So by the experience you will get to know what things to analyze or what things to optimize when doing what if analysis. It is just a manual study which will show you if you will make changes into certain parameters, what are the different results you are getting, and whether these results are going towards your whether your desired values or not. So, but I am not sure that my what if study is whatever the parameters I have selected are right or wrong, or I should go on changing the different parameters. So then I go for parameter correlation.
So this was regarding, the previous section was regarding what if study. Now once I have made a comparative study by varying all the parameters, now I'll go for its correlation study. Now the parameters which we have set and the output which we have obtained for those particular input parameters are being plotted in a graphical form. And based on the nature of the graph which we obtain, we undergo a correlation study. We perform a correlation study, and from that we come to know whether certain parameters are affecting the design exactly or are they not affecting your design. There might be certain parameters in your design which act as neutral parameters. For example, even if we change the value of those parameters, there won't be any change in your simulation results. Now those are called as independent. There are two types of parameters: independent parameters and dependent parameters. Now how this parameter correlation study helps. In particular simulation, suppose we have two variables, x and y, and those two variables are independent. There is no relation between those two variables. So what will happen is variable x and variable y will change independently. There won't be any relation between those variables. So we'll get a scattered plot. Now this creates a problem. Instead of those two variables, x and y, if there would have been only one variable in your simulation, that is x, then it would be comparatively easier to plot or to track the exact behavior of that parameter. Now, in certain circumstances, your simulation demands input for more than one variable. There might be two or three variables. So in those circumstances, if there is a correlation, if there is particular relation between those variables, for example, my x variable is equal to twice of my y variable, which is equal to thrice of my z variable. So in this case, I can simply target one variable, that is x variable, and I'll go on changing or modifying that variable. Based on that, my y and z variable will be controlled. So this is what is called as correlation analysis. Is it clear up till now?
So parametric correlation is nothing but it identifies the parameters that are being affected or different affected variables. So it will show which variables are affecting. You can see in gray color there are different zones over here: red zone, blue zone, gray zone. So gray color indicates that those parameters are not being affected. That is, there is no effect on these parameters when you do optimization. So you can see that red color indicates you can see this plot which is among input parameters and the outputs obtained by you. Okay, so when it is at a blue zone, you can see that this blue zone indicates that increasing input is equal to increasing output, or you can say that it is a direct correlation between input and output. When it is going towards the red zone, that is what you can see at this edge or diagonal, is called that is called where the maximum parameters are got affected at this zone. So this indicates when you increase the input, there is a decrease in output values. So this is the inverse correlation between input and output, which is shown by red zone. So it can assess the degrees to which the affect the input. So that's why we do the correlation or sensitivity study. It is like by doing this study, we can say which is the best suited design. And this particular study, that is sensitivity and correlation study, it is more suited when we go for multiphysics analysis, or we take objective type analysis or goal-driven optimization. So at that time, this study plays a crucial role. Also, it is helpful when we are doing the analysis of several independent variables. What we have explained the relation between x, y, z. That those variables were depending. There was some relation between x, y, and z parameters, and those called as the related. Those were dependent on each other. Similarly, you have some independent variable. Let us say I have three variables which are independent on each other. So, but as a mathematically, I can create 27 simulations for that. So, I need to, when I will do correlation study, I will have to run different 27 simulations for those three independent variables. So, for doing this, the ANSYS is capable of identifying the primary correlation, and it identifies the random sample point called as a Monte Carlo sampling. I guess you will be aware of this. So software, this is manually that this is manually that you will do this 3 simulations, 3 correlations. So by Monte Carlo sampling, you will get discretized parameters which are not in line. Those are spaced anywhere. Instead of that, ANSYS uses Latin hypercube sampling, where you are get evenly distributed parameters into a design space. But that is not here. Okay. So by sensitivity study, you can get a linear as well as non-linear graph. So what linear graph is? It will pick up the points which are in line. So linear study is comparatively easy and it is more appropriate. So we can tell you that you can go for a linear study instead of going for a non-linear curve which is shown by blue line. Instead of non-linear, you can go with a linear curve fitting. So as input parameters increases, your efficiency decreases and linear dependency. So it will give, where you will have a linear study, it will give a linear dependency between an input and output. So once we are done with the sensitivity and correlation study, you will get some results that the necessary address bounds of design envelope you will get. So once you are done with that, we go for design of experiments. So what design of experiment does, it specifies the design of experiment types. So what it actually does, it takes the vetted inputs from parameter correlation and distribute the sample point optimally within a bounded design space. So what it will do, it will specify each parameter range and time. It may be continuous, it may be discrete, or it may be a manufacturer value. So design points are automatically chosen to explore the parametric space efficiently. Once design of experiment is complete, we use a mathematical model which is the response surface to predict results at any point within the design envelope. So response surface is used to find the output of other design points which are used in design of experiments. So in design of experiments, design space is defined by lower and upper bounds of input parameters. So various algorithms to optimize the spread of the sampling priorities in a design space.
So as you can see here, the graph at the extreme left, this is your sensitivity correlation graph, which you have obtained by carrying various set of design of experiments. Here each and every point is the result of each experiment carried out on each and every parameter, which we call it as design of experiment. Now based on the scattered graph obtained from design of experiment, now the solver will explicitly trace the entire behavior of that, all the points taken into consideration, and based on that it will create a response surface. Now what do we mean by response surface? Basically it is a mathematical modeling which we have constructed or we have generated based on the output of design of experiments. Now this mathematical modeling concludes that for a particular parametric study, for a particular number of variables, this basic formula or this basic equation will give you the derived results. For example, the value of areas of ellipse, circle, triangle, rectangle, all those geometric shapes, or the pressure area formulas, can be derived using this response surface. First of all, the mathematical modeling, the formula of various entities are basically the mathematical models which are being developed or which are being generated carrying out certain experimental study, which we call it as design of experiment. So from this, actually, we can generate a mathematical model. Now, this generated mathematical model can be plotted out in various graphical formats, which makes it easier to which makes it easier to have a comparative study. Now, these graphical formats can be in the form of pie charts, bar graphs, or simple line plots. Now,
is there any doubt up to response surfaces? Is there any doubt?
Any query from any of the nodal center?
So, Monica, now I will show it on a tool. Fine?
Okay, ma'am.
over here, we'll take the example of same beam which we had earlier taken for our what if study. Now, the difference between the previous example and this example is that we are actually going to optimize this beam considering the factor of safety. Got it? So, as I told you earlier, we have parameterized the cross-section dimensions. Then we'll go to the model. Whereby we had parameterized the mesh sizing and we had parameterized the value of forces. Now, apart from the total deformation and equivalent stress, we'll just simply insert one fatigue tool. It is available right here. Under fatigue tool, I will insert safety factor. And by simply solving this, I got a plot for safety factor, which is somewhere around 2.1643. Now, my main focus is I want to optimize the design taking into consideration particular safety factor. For example, I want to design my beam model which would have that particular factor of safety. So I'll just parameterize that safety factor which I've obtained from the software. Now, I'll simply go to the toolbox and there's the option of response surface over here. I'll simply drag and drop that response surface onto the parameter set. So a response surface model will be created by the solver. Now I'll simply go to design of experiments. Here, as you can see, these are the two input parameters, height of the cross section and width of the cross section, based on which I am having one output parameter, which is my factor of safety. Now, previously we had seen in what if study, we were randomly assigning parameters. We had no idea how many iterations will it take from which value to which value. So over here, we can overcome that limitation by giving a range of values. For example, when I click one first input parameter, it will ask me for the lower bound and upper bound. I had set its value as 40, so I'll just try to alter that value from 35 to 45. So I have entered 35 as my lower bound and 45 as my upper bound. Similarly, I'll change the width of the cross section. I had entered the width as 30 initially. Now I'll alter that value from 25 to 35. Now based on that, once I click on this update, what the solver will do is it will generate the parameters starting from 25 to 35 for width and 35 to 45 for height. Once it gets updated, you will have a complete list of parameters over here. You can see all those parameter list. Right now it is updating. So what it will do is it will automatically trace the value of factor of safety for all those range of values. Once we obtain the factor of safety at different value ranges, we will simply plot a response surface for that.
So by the time it is being updated, I will just tell what we have done into response surfaces. We have mathematically submodeled that describes relationship between input and output. So we have done a mathematical modeling over here. What we had done into the what if study was totally a manual thing, and then we went for the correlation study, then we went for design of experiments, then we have come down to the risk. Then we have come to the response surface study. So in response surface studies, what software is doing, it is by the time it is doing a mathematical submodel that will describe a relationship between your input parameters and whatever the output you have obtained. It will also differentiate the algorithms to model the response surface to capture linear and non-linear effects. As in the previous slides, I had told you about a linear variation between input and output and a non-linear or a curved variation between input and output. So when we get the plot between input and output, basically input linear variation will give you the good results as compared to the non-linear variation. So what are the different verification points? So the good practice is to take the algorithm against the actual simulation results. So it is important to identify validity of the response surface before we go ahead and optimize this mathematical model for design. So once we are doing this response surface study, after response surface study, we will go for actual optimization. So response surface will indicate whether your study, whatever study you have done, whichever the response points you are considering are good enough, and whether you can take them to actual optimization, because the next step after response surface study is by doing the optimization. And once you are done with your actual optimization of the structure, you will go for Six Sigma analysis. So that will be the final, and the same design you can take to the manufacturing. So response surface plays a very important role into your simulation. So we can have the identified in the response surface, we will identify the relevant parameters, and we will develop a method to predict the output behavior of my structure. So it may be your performance, it may be your design, or what are your design for the output. So using this information, we can generate an optimal design for your structure. So it is taking some time to do. Yes, we will reduce some parameters for that.
So as you can see, it is taking a lot of time to update those parameters. So I'll just simply show you the relevant slides which we have prepared based on that result. So once you have created a response surface model over here, in design of experiments, we have entered certain parameters. Now, these parameters are being updated right now. So it will take some time. So I'll just simply take you to the further step. Once these parameters are updated, we'll go to the response surface. We'll double click on the response surface. And by double clicking on that response surface, it will browse us to the GUI of that response surface model. Now, in that GUI, there are various parameters which we have obtained from the previous analysis. These parameters are being parameterized, and once we click on the update button, which is available in the top left corner, once you click on that update model, a response graph will be generated like this. It is available at the extreme left hand corner. And you have an option for viewing that graph in one-dimensional, two-dimensional, or three-dimensional plot. Now the graph which is actually present over here is a 3D response surface graph. So you can also view it in 2D. That depends on your requirement. You can manually change the viewing type. So here we have set the viewing type as 3D. Now from that response surface graph, we'll obtain the optimization based on our goal. Now how to obtain that? Under object, there is an option of objectives and constraints below our optimization option. In that, there are three options: seek, minimize, and maximize. So for any parameter, let's say in our study we are focusing on factor of safety. So when you click on that parameter value of factor of safety under objectives and constraint, it will ask you for the type of objective. So if you want to minimize the factor of safety, then you can simply select on minimize. If you want to maximize the factor of safety, then you can simply select on maximize. But in our case, our goal is to optimize the design having factor of safety up to 2. So I'll just simply select seek in objectives and constraint, which can also be taken as a goal driven optimization, because I am setting a particular goal that my factor of safety should be 2. So based on that, it will show me the various value of various parameters where my factor of safety will range from 2.2 to 1.9. It means there will be a delta, plus or minus delta, near my desired value of factor of safety at those design points. So you can see over here, you will get the option for candidate points. Now the candidate points are actual design points. You can see there are three star marks besides those candidate points. Now what does this indicate? This indicates that these results are optimum. For candidate point 1, the value of the parameter value of 41.499 is the optimum value. Got it? And if you round off all the values, then you will get 41.186. So this indicates that at this particular value, my factor of safety will be 2. Is there any doubt over here? I can understand that it might be difficult because actually we are not able to show you the simulation. But are you understanding, or is there any doubt?
Hello? Hello? Can you hear me? Hello?
Yes.
Generally here, which method you are using to develop equations? And response surface method you are using to develop equations, which design of experiment technology you are using to develop the equations? Hello?
So it will automatically generate equation at the back end. Now,
What is
type of approach
that?
is using Latin hypercube sampling. So there are two types of sampling: Monte Carlo and Latin hypercube sampling. Now, what is the difference between those two sampling approaches which the solver uses at the back end to generate a response surface? Now, when you talk about Monte Carlo sampling, then the solver will automatically arrange the design points which you have assigned in a 3D graph. But the main problem with this Monte Carlo sampling is it might have same design points at two design points at same location. So the solver will independently evaluate for each and every design point. So it may happen that the same design point is evaluated twice. So this consumes a lot of time. Instead of that, the second type of sampling approach which we use, that is I talked about Latin hypercube sampling. What happens in that? It assigns one sample point in a 3D space, then it scrutinizes for the available space. Means it won't let that happen that two design points are within same space. So what is the advantage with this Latin hypercube sampling approach is each and every design point has been evaluated independently without any repetition. So based on that, the response surface is plotted. Is it clear now?
Hello? Hello?
Yeah.
Hello?
Hello?
It is from this note, so I have this basic other engineering. Which concept of the JE you applied to develop the model equations? What is the name of design taken to develop the equations and the RSM?
So those equations are being generated at the back end by the solver. So we don't actually generate those equations. It is a complete function of that solver.
I am asking, there are too many models are there are too many designs are there. Which design have you applied to develop the model equations for RSM? You can hear me?
We have used Latin hypercube sampling approach to develop those equations at the back end. Hello?
Hello?
Sir, we have used Latin hypercube sampling approach.
What?
Latin hypercube sampling approach.
Actually, in the RSM, there are 5 designs are there. From 5 designs, which design have you applied to develop the model equation?
Sir, that further optimization is still left. Right now, we are at the 4th step. Initially, we had undergone a what-if study. Then we went to parameter correlation. Now we are in response surface. After response surface, we'll go for topology optimization. So there is a complete flow of study for optimization. We are at the 3rd step now. After response surface, we'll go for topology optimization.
What? My basic question is, what I must mean, which design you have applied to develop the model equations on the response surface methodology?
So actually, I'm not getting your question. Is what you are trying to say? I'm not getting that.
Look, I can tell you, there is central comfort design, central comfort patient design, burst linking design, like that 5 designs are there. Which design have you applied to develop the equations for response surface methodology? To develop the model equations, you must have one particular design. Which design have you applied?
Pardon, sir?
Actually, you are saying that model equation has been developed to identify the better parameters, optimize the parameters. To develop the model equations, before developing the model equations, first of all, you must select the best design. Which design have you selected to develop the model equation?
So that is a function of the solver. That depends on the solver. Solver is using certain notation.
Going to the computer and getting the data, but there's also a name is there. What is the name of the design you have applied there?
Mekal, can you do one thing? Can you just set his mic properly because we are not able to get his sound properly.
Then sir, I type on the question in chat box. Which design have you selected to develop the equation? Can you say any name?
Design is not clear. One more question is, you are saying that the answers, what is the purpose of the answers?
So can you please come close to the system?
To develop the alpha values. Is it not okay?
RD College? RD College, sir, can you please come close to the system?
ఢిల్లీ నుంచి వేరే వాళ్ళు ఇస్తారు సార్ సో స్టూడెంట్ వచ్చినప్పుడు ఢిల్లీ నుంచి ఇంకొక ఏసీ ఇస్తున్నారు వాళ్ళకి ఆంబిగ్యూటీ వచ్చింది క్వశ్చన్ చూసి ఆన్సర్
Chat box where we can see
క్వశ్చన్ చూసి ఆన్సర్ చేస్తాను క్వశ్చన్ వాళ్ళు అండర్స్టాండ్
Yes, sir is coming close to the system. Now I guess it is audible.
ఓకే
will you tell me?
Ma'am, sir is answered the question in the chat box.
Yeah, fine.
So, hello?
Yes.
Hello?
Develop the optimal parameters. Okay.
Actually, the answers has been used to optimize the parameters. Is it okay?
I'm selected develop. Can
You have developed to optimize the parameters of the answers. The same parameters you have taken in design of experiments, still you develop the model equation using response across probability. Find this, after this, again, you find active values. What is the use of finding active values to the two types? One from answers and one from design of experiments?
Design is part of answer. So as you can see here, I can show here that I have done some analysis by taking some structure. Now, whatever the output, now let us say I want to optimize a design because the results what I am focusing is, let us say, factor of safety. I am focusing that I should get factor of safety at exactly 2 value. So for getting that, ANSYS is having, if you will see ANSYS, there are different 4 tags are there. One is analysis system, component system, custom system, and the most important what we are talking about is a design exploration. So for using design exploration, first you will have to do your simulation in any of the, let us say, structural simulation. It may be your CFD or flow simulation. By doing that, you will get some results. Now I want to parameterize that. For that, I am taking a design exploration. In design exploration, you can see on the screen that I have direct optimization method, I have parameters correlation, I have response surface optimization, and the last step is a Six Sigma analysis. So, optimal design, direct optimization is what we were talking about OTIP study. That is your manual study, that you can manually optimize your parameters. Now we are studying here the response surface. So in design exploration, what are different softwares or different methods available to do a optimization study are we are explaining. Because the session is based on the optimization techniques. So what are different optimization techniques available inside ANSYS that we are discussing. So few we explained on slides, for few at the first version we did what in a direct optimization, where we manually did the optimization.
Actually, here both are virtual systems because you are using only the ANSYS, second one is the design of experiments. You are taking the data from the ANSYS and also the same data you are using in design of experiments. There is no
Yes, sir.
real data.
Yes, sir. Honestly, and this platform have these word tags. So entries is mainly answers handles all different types of physics. If you can see that, as sir has told me that different faculties from different departments are there. So here in analysis system, you can see here structural, as fluid flow, we have magnetic status. Again in electromagnetics, we can answers can handle low frequency as well as high frequency. So even in thermal analysis, different types of analysis can be handled in the ANSYS. Also, you can use a multi-physics that will one physics is dependent on other physics. So such kind of simulations in the further slides you can see such kind of cases are possible in ANSYS. So in ANSYS, workbench on the same platform, you are doing analysis for doing optimization and putting one more study that is under the design exploration. I have different studies that I can optimize my design.
So we can, by using workbench, we can get the parameters from many sources. For example, we can build up the parameters or we can extract the parameters for our study by using 3D CAD design. From structural analysis, mechanical structural analysis also, we can get parameters. We can get parameters from CFD flow analysis and as well as from electromagnetics. So these are the various platforms which are used for analysis from where we can extract the parameters, put them into a set of design of experiments based on which the solver will give you the actual response surface curve. This is the basic overview. First, over here, first we have performed a multi-physics simulation which consists of a fluid flow and a structural simulation. So it is a case of FSI over here. So over here we have taken certain inputs from fluid flow analysis and also from static structural analysis, which has created a parameter set with all the parameters in the form of tabular format having all the design points. This is what we were talking about, what if analysis. Now, after performing what if analysis, this design exploration has a three-step workflow. First, we need to plot out the response surface from the design of experiment, which we have discussed. Now, once we have performed the design of experiments and we have extracted the response surface out of that, the fourth step is response surface optimization. We actually perform optimization based on the values which we obtain from the response surface. Now, after that, this I think we have already done. Now, once the response surface is extracted, there's an option for optimization over here. In optimization, it will ask you for various optimization methods which we need to select. Now, it consists of various parameters. And those parameters are given certain input values based on which we get the graphical plots over here. So this is the response surface which we obtain by updating the design of experiments. And you can see over here there is a 3-star besides the pressure magnitude field.
Monica, will you please shut off your speaker?
Yes, ma'am.
Actually, will you please shut off the speaker button at your place because we are getting the same repeated noise.
Yes, ma'am. Maybe. Okay, ma'am. I have to switch off my mic instead of speaking.
Now you can see over there, there is an option over here. I was talking that you can plot the response surface in 2D and 3D plot. So you can actually select your visibility plot from this drop down menu. Now over here, pressure magnitude and the extruded command and equivalent stresses. These are the 3 candidate points which we have taken for our parametric study in that example. Now over here, the results of optimization are showing that the pressure magnitude is the optimum parameter which we need to take into consideration for that particular type of analysis. You can see a 3-star mark over here. And similarly, you have a single star mark besides equivalent stress. And extrude is not having any mark. This indicates that this is the least concerned parameter with regards to that simulation. This is unwanted parameter. We don't need to focus on the extruded depth of your 3D CAD geometry to optimize that design. So it depends entirely on the magnitude of pressure which we apply for our simulation. So this is what is called as goal-driven optimization, wherein we have set the value of the desired output which we require. For example, if you are taking into consideration factor of safety, I have set the factor of safety as 2. So based on that, the solver will tell me by changing the pressure magnitude to so and so, I will get the desired factor of safety. Got it? Now once you are done with your simulation, you can export those results to attach that into your reports. So how to do that? There's an option under file whereby you can select the export report option, and it will just give you a PDF file which contains all the informations about the analysis.
Monica, I want to know how much time is left, whether I should discuss the case study or not. Monica?
Yes, ma'am. And 5 minutes are left.
Okay, only 5 minutes. Okay. So I will take just a simple example that how it is being. So we are actually talking much about the theory since last 2 hours. Yes. Yes. Pardon.
Any question from any of the nodal center? Soba Saria College? No, ma'am. No queries. You can.
Yeah. Yeah. Fine. So I will just discuss two case studies which is on different physics. So first I will discuss the optimization of the aircraft on the flow parameters, how the aircraft is being optimized. This is we have done for one of our customer. So actually the aim was to develop an aerodynamic design which was based on a numerical optimization of a complete transportation aircraft. So for this particular thing, the numerical study, the analytical study was done before. Now we want to see numerically that on to answer software how this study is going to happen. So numerical solution was required in order to investigate a huge design space in a fastest way possible. As I told in the beginning only, that analytical and your experimental studies take a long time. Instead of that, we will go with a numerical study. So how we did the solution for this particular case? This was a transportation aircraft. As I said earlier, for particular aircraft, I should have high strength to weight ratio, and we should have a good aerodynamic shape so that my body should sustain in a free air, that is, and it should move as fast as possible. To move it in a fast, you should have a proper aerodynamic shape or aerodynamic profile. So I had some CAD model with me. Then I did it in ANSYS Fluent and ANSYS ICM CFD tool. In that, I analyzed my structure and I analyzed the fluid flow, that is air flow, onto my structure. So you can see the first body, that this is just a wing body configuration of an aircraft where you can't see any winglet onto it. When I started optimization, I had a optimization on different aspects, that is a body configuration. I had a wing body configuration, fuselage wing configuration, and then taking the whole assembly in a configuration. Next was, but to that configuration, I first did the optimization. I got some optimized structure to it. Once I have got it, I have assembled one winglet to it. Now, for size and shape of the winglet, we have done the optimization. In the next structure, we have added the control surfaces at a tail portion, that is a horizontal tail as well as a vertical tail. So now my aircraft is configured with my wings, my winglets at the tip of my wing, as well as my control surfaces at a tail, that is a vertical tail and horizontal, as well as here I have put all the control surfaces, that is horizontal stabilizers, radar, elevators, ailerons, already I have attached to it. Once we are done with the whole structure and fluid flow analysis, we got some optimal structure for this configuration. Now next is the most important thing, when we assemble engine to my aircraft structure. When we assemble engine to it, engine will again have some specification. Again, your engine should have a streamlined body pattern. So what are the then? Engine will have some input values of pressure, velocity, density, and it will exert a huge amount of thrust which will move my aircraft in a forward direction. So once I will assemble all these things, again I will go for optimization, that is the positioning of engine, where the engine should be placed. Always you can see in most of the commercial aircraft, transportation aircraft, you can see the position of engine on a wing. It may be most of the time you can see it on a lower portion of the wing. So if it is an Airbus 380, then you can see that there are two engines assembled at each wings. So what should be my position? So I will go for distance. I will manually take different distances and I will optimize whether what strength, if I will put my engine at some particular position, it should not affect the strength of my aircraft. So we have done optimization for this. This is a aerodynamic optimization for the same case study. We have done optimization for the structures as well. As I said earlier, it may be for your material, it may be your material, it may be shape, it may be the size and shape of your inner parts in the aircraft which strengthens your aircraft. So then by doing the optimization study, we got higher quality aircraft design was found that satisfies design and safety constraints in the relative short period of time. So here in this study, if you will follow the optimization study into ANSYS, you can optimize your design in shorter period of time. Similarly, here is an example of optimization of brake. So most of the time you can see the warranty when we talk about brake manufacturers. They are more concerns about the warranty cost. So they want to reduce the warranty cost. So how it can be, sorry, how it can be reduced. So this is an example. So most of the brakes you can see the noise is a very important issue in all the car OEMs and suppliers. So the most important factor was to reduce the noise. By reducing the noise, I want to reduce the warranty cost. So what was the ANSYS solution given to for this particular is, we developed a parametric and persistent simulation data which provided faster and accurate brake sequence solution for multiple design configuration. We changed on which parameters we did the optimization study was a brake friction and pressure and the material properties of brake pad and the manufacturing tolerances. So we took into consideration these all aspects. After the simulation are done, the parametric study was done and did. So it also automatically simulate many design points quickly, and it iterated a brake design that was meeting the noise requirements what I was wishing for, and it was giving a combination of best performance for cost, weight, size, and other factor what the customer looking for. So I wanted to show one video, but I will just tell you how you can do the topologization or topology optimization system. As I have, we did in last some time we were doing the design explorer. There is one more tab into ANSYS systems is called as a topology optimization. In topology optimization, you optimize a certain parameter into it. So you can make, if you can see here at the last row, you can see P is written. So P is nothing but parameterization, or we are optimizing some particular parameter. That parameter may be geometry, that parameter may be your boundary conditions, that may be your mesh quality. So instead of, if you are going for small scale applications of optimization, so I will recommend you should go for topology optimization. If your structure is huge enough, there is assemblies of different parts, then best to go with design explorer, which will give you optimum results for the best suited values. So I will just summarize this. So optimization is nothing but a range of condition and design parameters within a single environment, leading to enhanced product performance and integrity. So if you will have, we will obtain optimization through the simulation in ANSYS, you can meet the values what you are looking for, what you are desiring for. As a simulation company, our success is based on your satisfaction. That is, if you are getting a optimized design through simulation, which will save your time as well as cost. So in this analysis, what if you are doing optimization, what are the results or what is the design impact you are getting? And you can get the product performance faster, your product performance will be faster, that we can ensure, and we can, by doing optimization, you can enhance the product performance. Also, you can increase the development speed. As I said, analysis will not take much time as compared to your other methods that you are doing a hand calculation or any of the experimental values. So this particular thing, analysis will not take your much time. It will reduce your time as well as cost, and it will also reduce your warranty costs. Is there any question?